So today we're doing Lyapunov stability. Okay, so last time we finished with this Kepler's laws. So this is the last item of this course, as I was saying. So first of all, so we did stability of equilibria for nonlinear ODEs with that thing with the eigenvalues, okay? So the idea, the main idea in there, right, the core, the essence of the method is that near an equilibrium, we can approximate something that is curved or whatever, you know, not linear with lines, okay? So we approximate the system with a linear system, and thus knowing how to solve a linear ODE system, and that's where the method comes with the eigenvalues. We can deduce from the, you know, the sign of the eigenvalues, the sign of the real part of the eigenvalues, if an equilibrium is stable or not. So that's the essence of it. Approximation near an equilibrium by something that is non-linear by a linear system. Now, this method today is quite different, okay? So it's an energetic method. It relies on a different kind of mindset. It's in a different mindset setup, okay? So first of all, I'm gonna remind you what stability means, okay? So there you go. Let's say we have an ODE system, okay? And it can be in higher dimensions. So X is in some open set in Rn, okay? I could make it like vector if you want to, I don't care, okay? And then we have X of t is a constant Xc is an equilibrium, right? So an equilibrium meaning that it would verify that the right-hand side is 0 when we substitute. It's a root of the right-hand side being 0. Okay, so now this equilibrium, so an equilibrium, Xc, okay, is stable, okay, if for any neighborhood of the equilibrium in D, if you want D, okay, there is another neighborhood. So first I'll write it like this, such that any solution that starts in V, any solution that starts in V stays in U. So I'm gonna put this in quotes, and then, you know, we'll write it. I won't write it really with epsilon and delta, but, you know, I'll write it more like with math terms. Stays in U. Okay. So in other words, okay, any solution with X at t0. So this is the initial condition, right? Condition here. Maybe I should put my glasses on. Condition. Okay. In V fulfills X of t is in U for any t greater or equal than 0. Okay. So obviously this V, you know, has to be in U as well. So I prepare some pictures for you. So in 1D, the picture would be like this. So here is the axis of time, and this is the X as it evolves, right, in time. And then we have the X of t, Xe as the equilibrium. So the equilibrium is basically a line, it doesn't move, right? So X of t equals Xe, right? It stays the same for all times, right? So there is no dynamics, no motion there. All right. So that's Xc. And now the definition says that for any neighborhood, so I'm going to take any neighborhood of this Xc, so any interval, okay, that has Xc inside, and I'll make it open, okay, so any U in here, or any U there, there is another neighborhood, so let's make it light blue. Here, let's say this V, okay? So that whatever starts in V, okay, so what color should we take? Purple. So whenever I have an initial condition in V, I will just do whatever, but I will not go further than U. So let's make sure that we understand what the neighborhood U is. So the neighborhood U would be like this slab, okay? So all this slab here, okay? So whenever I start in this V, I will not get out of the slab, okay? I cannot also cut the red line because this means that I have two solutions, distinct solutions that pass through the same point, and we are working in a world where you cannot have that. So every solution has its own past, right? Every individual has its own future, okay? You know. So the solution is unique. So if I start here, I can go all around, but I don't go out of that slab, okay? So this is x of t. It stays in U for all t positive, okay? And it starts in this is happening for any solution that has the initial condition inside this V, okay? So that would be x in t0, okay? They go there. Now, if I start somewhere else, this is not guaranteed. I might go haywire, okay? So that's not the case, all right, for whatever starts in V, okay? So there's the picture in 1D. Now I'm gonna make the same picture to understand the definition in 2D, okay? So I repeat, the purple curve cannot cut the red curve, because if they would cut, this means that you have two distinct solutions that are at exactly the same place at the same time. And this means that you don't have a unique solution. So uniqueness means that different solutions are at different points at different times. And they cannot be, because if they coincide in one point, then they coincide everywhere, okay? So that's why I cannot cut. If I start with the solution down here, then I can stay in the slab as well, but that will be on the other side. Huh? It will be like here. Okay, so that will be another x of t. Okay. All right, so this means stable. Okay, that's the picture for later. Now in 2D, if I want to make the picture of stability in 2D, and I insist these are important concepts, you know, as we're talking about concepts. In 2D, we would have something like this. Okay, so I kind of did it. So we have an X, Y, and up is T. And then here I have to make a nice, and then I'll do the Y axis. I just leave it for later. So this is the equilibrium. Okay, maybe I'll do it with the, okay, that's the equilibrium. Okay, it's the same position for all times. Okay, and now whatever neighborhood, let's see, what color did I do? Green. Whatever neighborhood I take off this equilibrium, so here is a neighborhood, I'm just making this. And actually, okay, make it half, 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 and then the other half we won't see it. Okay. All right, so when we say neighborhood is like a tube now, it was a slab in 1D, in this case is like a cylinder, right? So it surrounds this fellow. So whatever neighborhood we take of XE, we find another neighborhood. So we did it with lights. Okay, so we find the V. There is a V. So this one is inside. Well, I should do it with fine lines. Okay, so that if I start in V, okay, I go around, but I don't get out of the green tube, if you want. I don't get out of U. So I repeat, the green tube, this guy, this is the U, okay? The light blue tube, right? So this area here, right? And as it goes up, as it goes up, right? This fellow, this is the V. So whatever U, a neighborhood of the equilibrium, there is V, change the color, there is a V, a neighborhood of the equilibrium, such that if I have for any solution with the start, right? So it starts in V, okay? We have that it will stay in U for all t. Okay, so now when I'm starting in V, but I go around, but I don't get from the U. So I could get like this, whatever. Okay, I can do whatever. Okay, something like that. Okay, I think it's clear now. For the 3D picture, it should be quite all right. All right, so we can go around. So this guy down, this is X, oops. Let's obey the color code, X in T0. And then this is X of T, right? So X of T just stays in the green tube. That's what it means. And obviously the time, so now I can put this other axis in. Okay, so that's why, right? And the time goes up that way, right? So as the time goes up, it goes this way. Yeah. Okay. All right, I think it's clear what stability means, at least in picture. We can write it in epsilon and delta, but I stay away from that, you know, it's okay. If you understand the picture, it's fine with me. And we have also the notion of asymptotic stability, and that would mean something a little bit more constrained than what we have here. So here is definition, X of T cos Xc is asymptotically stable, okay, equilibrium, okay, if for any neighborhood of itself we have that any solution that starts in there with initial start in this U fulfills that any, we have that any fulfills limit of X of T, it's asymptotically tended to the equilibrium. As T goes to infinity is 0, okay? So if I want to do a picture for this, would be not that purple thing, not that it stays around, this actually lies down, aligns itself with the equilibrium, with the red line in there. Or if you want in 1D, I will not do the picture in 2D. In 1D would mean something like, okay, so. Okay, so let's go a line here. So that would be the T. Okay, let's do the XC. line here. Okay, so this is x, oops. Okay. X of t is xc. Okay, so that's the equilibrium. And now whatever neighborhood I take here around it, and I start in there, okay, it doesn't really matter if I go a little bit further this time. What it matters is that in time I will just asymptotically align and tend to this guy, right? So I will have that x of t, the distance between x of t and xc, as t goes to 0, t goes to infinity, this goes to 0. That's the idea. Okay. So that's for a solution. Here, if I take another one on this side, again, I can do whatever, but then I should make sure I'm doing it nicely. Okay, but then at some point it's just, again, the same thing. Okay. All right, there you go. That's the idea. I think you got the idea. Okay. Okay, so that's stability. And now here is this criterion. Actually, we don't start with a criterion, we start with another definition. Okay, so let's do one more page here. So first, I'm going to define what is a Lyapunov function. So consider, let's say we have an ODE, x dot equals f of x, and xe to be an equilibrium. Okay, and here x is in some domain open in Rn. Okay, so here is the definition. A function w defined on some u naught goes to R, where u naught is a neighborhood of xe, okay, is called to be a Lyapunov function for xe if, and now here are the conditions. 1, w in xe is 0. 2, w of x is greater equal than 0 for all x in u naught, and w of x is 0. Okay, that's it. Okay. And 3, w of x of t is decreasing. Okay, I like to write it like this because that's how I remember it, is going down along for all x of t solutions for all paths, let's say, that are solutions of the equations. Okay, such that, let's say, x of t is in u naught. In this way, we're correct. Okay. Path, right? So the product for all x of t paths, for all paths that are solutions of the equation, right? So the equation star, let's put a star on it. okay? So there are these three conditions, okay? All right, we will not work with this one. We will work with an equivalent one, okay? So W of X of T is decreasing, and actually I should say n continuous, put n continuous, because I'm not thinking necessarily that right now is actually differentiable. We'll work with it differentiable, but for now, let's just put it like this. Okay, so the main result or theorem that we will apply tells us that if we have a Lyapunov function, so you can tell that this guy was Russian, right? Lyapunov, okay? So if we can find the Lyapunov function for an equilibrium, then what will happen, we'll prove it in a second, then that equilibrium is stable. Okay, I mean, that's what it is. So we will have a very strong method to check stability without eigenvalues. Okay. So let's see, I prepared the picture to give you an idea how this is proven. So what is here is, okay, so it would be this theorem, okay? So if XE, an equilibrium, right? So if an equilibrium X of T equals XC, of an ODE, blah, 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 admits a Lyapunov function, then it is stable. Okay? And I'll show you how to apply this theorem. For the moment, I want you to follow me in a sketch of the proof, okay? And the picture is related to this sketch, okay? So I'm waiting for you to finish writing, okay? And explain to you what is this picture. We're gonna just follow the picture pretty much, okay? So here how it goes, right? So I said, okay, I'm working in 3D. So here an X actually means is in R2, so it's in an XY coordinate, okay? So an X, I'm putting on purpose the vector symbol on top, so you'll know that I'm talking about a quantity, a vector with two components, okay? So what do we know? We know that there is a function that is zero in the equilibrium. Here it is, the zero. Here, I'll start beefing with red. So it's zero in the equilibrium, is greater than equal to zero when we're not, from around the equilibrium, they're in a neighborhood. And it decreases when we calculate it along any path that is a solution of the ODE. Okay, so let's see what I drew here with this blah, 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 right? So with green, I try to sketch a function, W, right? So W is like Z, see, Z is W, Z is the height, input XY, height is Z, W of XY, okay. So here is this ballish thing. So on purpose, I made it, that is not all around the ball, okay? So what we know for sure that around the equilibrium, which is here, is down there, this function, right, this ball, is zero, so touches the base, right in here. And then is going up nicely, right? And we have this neighborhood that it stays, it keeps it there, blah, blah, blah. All right. So the proof goes like this, okay? So basically, what do we have to do? Okay, we have to consider a neighborhood. So let U be a neighborhood of the equilibrium. So here is U is this bluish thingy, okay? So what we want to find, want a V, okay, which is again a neighborhood of the equilibrium, such that whatever starts in V doesn't get out of U, right? So when I'm starting in V here, so this is an initial condition in V, I'm going with my solution where I'm going, but I better not get out of U, okay? So I might do something like that, right? So I trace it on the bottom, right? It's not on the top. Time is not on the top. On the top is the height of this W, okay? Excuse me a second, I have to kick a dog out. He's moving around and that's a sign of something, okay? Hi, Mama, hi. Mozart is in the back. Well, he was moving around and, you know. Okay, let's move fast with this thing. All right, so we want to find a V, okay, a neighborhood. Okay, want. Such that whatever starts in V doesn't get out of U. Okay, that's the idea. All right, so I could research that any solution starting in V stays in U. Okay, stays in U. All right, so the idea is the following. Look, you know, I'm going to take the boundary of U. Here is the boundary of U, is this thick one, okay? And then on the boundary of U, when I'm calculating W, so I'm calculating up, right? So this trace here is actually the values that W takes on the boundary, on this boundary of U. So if you want here. So this one goes into this point, right? And this one goes into this point. So this is basically this thing here, right? This edge is W, is the image of the boundary of U, if you want, okay? Of that edge. And then I'm taking the minimum value that W takes on this edge, you know, because it could go up and down. I'm taking the bottom one and I'm calling it M, okay? And then because I know that W is positive and is 0 here, right? I know that I will find the neighborhood around XC here for which W in all this area that is here. So again, you know, this guy maps into here, this guy maps into here, and the interior, right, is on the edges of this ball. So all this stuff here, right? The values of W here that are, you know, from the reddish patch on the bottom, these ones will be less than M. Okay, and I know that such a thing exists. So now the idea is that, look, if I will start inside here, inside V, okay, I will end up with the point up here. And from here, the only thing I can do, because W along any path is going down, this guy will have to go down the trace of it, right? So this is W of X of T, because if it doesn't go down, okay, it has to go down by hypothesis. And then this will imply in itself that if I'm looking at the path and calculate the values, these guys will not go away. That's the main idea. So these things will have to be lower and lower, because otherwise you have to have a value higher, and then having a value higher, you contradict the idea that actually this function goes down. So that's more or less a kind of a sketch of a proof, okay? So the proof is actually the picture in a way, okay? So I don't want to insist more on it, but again, what I want to say is that this condition that this W goes down along any x of t solution, okay, this thing ensures the fact that, you know, once you start in V, you'll have, you know, you go up here, but then you have to go down, and going down ensures the fact that you will not leave this U, because if you leave U, this means that you're going to have values above the minimum of the edge, and then, you know, you're just getting into a mess there, right? You get a contradiction, as we say. Okay. So this being said, I don't want to kill you more with the proof or anything. You know, this would be in the next course, right? And if we offer dynamical systems, that will be done there properly, okay? So what I want to do with you, I want to do applications and also show you, right, actually the criterion. So here it is. This is what you're gonna apply. So the Lyapunov stability criterion, okay? And I'm calling it, it's a little bit, so this would be more, this condition is more general than the one I'm going to write, but the one I'm going to write now is the one we apply. So let x of t, xc, be an equilibrium, okay? If w, okay, of xy, oh, not of x, if w of x, w of dot is let's do that. If there is w defined on a neighborhood of xc such that one, w, the first two conditions are the same. Two, w of x is greater equal than 0 for any x in u naught, and 3, dw, a dt along x equals xt, okay, where xt is any solution. So along any solution, maybe that's what we would write it like, along x equals xt solution is less equal than 0, then xc is stable. If, moreover, okay, if actually not, okay, if, let's say 3 prime, dw, a dt at x equals xt solution is actually strictly less than 0, then x of t is asymptotically stable. Okay, actually here I have to put this, of course, everything has to happen now when I'm teaching, isn't it? Just a second. Well, it stopped. Okay. All right, so yeah, w of x has to be greater than 0 strictly here as well. Okay, just correct that, because I don't know what I was thinking about. Here, it's strictly positive, yeah? It's exactly a ball, strictly positive. Strictly positive, okay? Strictly positive. So, see, when I'm writing this, so this is the third condition instead of w of x of t decreasing, but this one implies that actually w of x of t is decreasing, okay? So in this case, we have a function that has to be differentiable, isn't it? Whereas for the other one was like w is decreasing, but can be just continuous, right? I didn't ask anything about its smoothness. Okay. So it's either these three, or if actually you have strictly negative, then it's asymptotically stable. And with this being said, let's do 2 exercises, okay? So you know how to do them, because that's what you're interested in right now, right? Okay, so I have here, closed it, huh? Okay, so, all right, so let's do this exercise. Okay, so let's say x dot is y dot is minus x minus y, and show that the equilibrium 0, 0 is stable using a Lyapunov function, or the Lyapunov function, w of xy is x squared plus y squared. Okay. Is 0, 0 asymptotically stable? Okay. All right. Solution. Okay. So we have W defined on, I guess we can take it on R cross R, goes to R. So all this stuff will be U naught, okay, in this case, just because, you know, as I look at it, so if this is x squared plus y squared, right, obviously we have the W in 0, 0 is 0, check. So that's 1, right? 2, W of xy is x squared plus y squared. This is positive for any x, y, if you want, that is not 0, 0. Check, right? That's another check here. Check 1, check 2, right? And 3. Now we have to do dw a dt along, right? X of t, y of t solution. You're going to say, but I don't know solution. But this is exactly like the energy computation, if you remember, conservation of energy. So this will be dw. So if you want, here, let's make it like this. This is dB dt of w of x of t and y of t, right? That's what I mean. So now we have to do the chain rule. So it will be dw dx dt plus dw dy dt. Good. Which is, so dw dx is 2x times dx dt, I'm looking in the system, times y, yeah, plus. So this guy is dx dt, yeah, and this guy is dy dt. Plus 2y times minus x minus y. Okay, so this is 2xy minus 2xy minus 2y squared. So this is minus 2y squared. Obviously strictly negative for any xy which is not 0, 0. So this means that 0, 0, not only that is stable, is asymptotically stable. Done. So if you want to check, you didn't have to do much. But on purpose, I picked it easy so you see how it works. Of course, it works nicely when we know the W, right? If someone gives it to us, it's just a verification. The question is, what do you do when you don't have W? Well, kind of guess it, okay? But that requires certain skill, right? Usually W is chosen in relation to the energy in the system, because the energy, it either stays constant, in which case, you know, we can say that we have a stable equilibrium by this criterion, or decreases because the energy dissipates usually. That's exactly what is here. This is a dissipation thing. This system is an oscillator with friction, actually. So the energy decreases, so the equilibrium becomes asymptotically stable. So the system goes to the state in which, you know, there's no more energy and just freezes there if you want. Okay, so that's the thing. Okay, so let's do one more exercise, a little bit more complicated. Okay. So of course you're gonna ask, so how these exercises are getting complicated? Well, just put a parameter in it, huh? Or just say, oh, I don't know what W is. Okay, so of course that won't be the case for us. Right? So here I picked this exercise because it is from the list of recommended problems. The other one was as well, right? Just because, you know, it's more algebra in it, you know, it gets a little bit more complicated. The idea is the same, right? We just have to verify 1, 2, 3. That's it. Okay, so the first question is, what is the equilibrium? And then study its stability, okay, using a function of the form x squared plus alpha y squared, whereas alpha is some real number that we have to determine, perhaps. Okay. Okay. So now to determine the equilibrium, we have to do the right-hand side equals 0. So I wanted to show you something related to this. What do you do when you cannot solve something by hand? Because here, no matter what I do here, let's say I do y is sine of 3 of x, and it gets to be weird, and I end up with an equation that is something like minus 4x minus sine of 3 of sine a 3 of x equals 0. Isn't that weird? Sine of sine, right? So even if I write it with plus, it's still weird. 4x plus sine a 3 of sine of 3 of x equals 0. So my first guess would be that, you know, whoever set up the problem made a typo. Let's assume it's not a typo, okay? So I don't know. So what do we do? Well, for this kind of stuff, what I recommend, okay, is the so-called the graphic method, okay? And the graphic method is consider the function f of x 4x plus sine of 3 of sine of 3 of x, and get Maple or something or your calculus skills and sketch it. And from the sketch, you will know if you have roots or not, okay? So in this case, okay, so we can do Maple because you have access to Maple even during the exam, right? Or whatever, Symbol Lab or something. So I did that, and then we end up with the picture. You know, this thing with using Maple for graphing is acceptable, but is not rigorous, because a rigorous method would involve doing the sketch of this function using the methods of calculus 1 with the first derivative, the second derivative, the asymptotes, all that stuff that was like a paraphernalia of stuff that you had to do in order to sketch a function, okay, if you have any memory of it. For our course right now, it's acceptable to just do a sketch with something. Okay, so here I did that, and you know, the 0, 0 solution, x equals 0, that we kind of, you see my screen? Yeah? Yeah, okay. So I just plotted, this is the function. Okay, so let's do it with plus. Okay. And here it is. It shows that it has a 0, x equals 0 solution that we would have seen it by just looking, you know, at the x equals 0 verifies 0, right? But the question is, does it have any other solutions? I don't think so. Here, it just kind of looks the same no matter what we do, right? So we'll just believe them. Actually, it's also kind of not easy, but you know, we can think about it because here we have the 4x. I'm trying to make your picture bigger, just a second, see? So here, what do we have? We have 4x plus sine of sine, right? Well, x is increasing linearly, is a line, and then sine, it just fluctuates, right? It's like blah, 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 in between -1 and 1 all the time. So you add something that is bounded, you apply to it another one that keeps it as bounded, and then you know you have x that is increasing big time, right? So yeah, it might be small near 0, but then x will dominate the entire shebang. So there is no way that x will cut the 0 axis anymore. I'm saying that you can think like it in this way. Anyhow, so let's go back to what we have to do. All right, so here it is. Good. So from Maple, we deduce that x equals 0 is the equilibrium. Okay, x is 0, right? So then we go to the y, but y was sine of 3 of 0. So y is 0. So we end up with 0, 0 is the equilibrium. Fine. Yeah. All right. And now let's do the stability, right? Stability. Okay. With the Lyapunov, like they say. So let's take W in Z. So I'm writing it again. Alpha is not specified. We're kind of looking for that alpha that would do the job, right? Okay, so this is W in 0, 0 is 0. Fine, good. Now W in xy is x squared plus alpha y squared. Now this will be positive for any alpha positive, right? So we're gonna say, so alpha has to be positive. So we can check, so condition 2 is verified, right? So if alpha is positive, condition 2 is verified, right? So we have 1, 2. And now we have to deal with the third one, which is the most delicate one, especially in this case. All right, so let's see what do we have if we do it dw or dt along the flow. So it's dw dx, dx dt plus dw dy, dy dt, yeah? And now we have to substitute. So, and I have to flip the page. Okay, so I'm flipping the page. So dw dt, right? So I'm going to write it again here, x squared plus alpha y squared. Fine. So it's 2x, okay. dw. I'm going to write it, you don't have to do it again. I'll just put it here for the benefit of everybody. Okay, so this will be 2x times, now dx dt is y minus sine 3x, yeah? Yeah. Plus dw dy, it's 2 alpha y, and then minus 4x minus sine 3y. Yeah? So we end up with 2xy minus 2x sine 3 of x minus 8 alpha xy minus 2 alpha y sine 3 of y. Okay. And I'm going to make my life very easy by canceling this guy and this guy, choosing alpha to be 1/4. Huh? If alpha is 1/4, then we have 2xy minus 2x sine 3 of, okay, let me write it again. Okay, 2xy minus 2x sine 3 of x, then minus 2xy, yeah, minus 1/2 y sine 3 of y. Oh, I have that. Not on the screen. Okay. So we end up with minus 2x sine 3 of x minus 1/2 y sine 3 of y. And it's unclear for now if this is positive or negative, right? So we have to think about it for a second. And that's why I chose this exercise, right? How can we do this? So we're interested in the sign of these guys, right? So sine, okay? I mean, it's easy to say, oh, they're, you know, positive, so overall we get negative. Well, I don't know, right? Okay, so let's introduce, you know, let's study this function. Let's say f of x is x sine 3 of x, okay? And let's think how this function looks and what it is, okay? So as far as I know, right, and everything has to be around 0. We don't have to go far from 0, right? Everything has to be in a neighborhood of 0. So this is actually the function y equals x. And then I'm going to draw with something else, sine of x, right? So sine goes from 0 to something like that, right? Okay. And then it turns around, huh? Something. So this is y equals sine of x, yeah? And if we do sine 3 of x, kind of looks like sine of x, right? Because you just multiply it by itself 3 times. So it has a kind of the same aspect. So this would be the same, at least, you know, sign-wise, okay? Okay, so now what we're interested in is what is going on in a neighborhood of 0. So what I'm drawing here, so I shouldn't say y, maybe I should put a different letter like Z, huh? Okay, so this is x and this is z, okay? Z is f of x, because it's not the same y from the next line, okay? So what we're interested in the sign of x times sine of 3 of x in a neighborhood of x equals 0. So I put the neighborhood with red, okay? And now we think like this. If x is positive, then for x small enough, as we can see in the picture, we have sine 3 of x positive, right? I mean, it's these guys here, you know, so this is the part that I'm talking about. It could be even further, but I'm not interested to go far. And this part here, right? So they're both positive. So if they're both positive, right, this means that their product will be positive for x small enough. Okay. So basically for x small enough, this sign here, so this will be positive for x small enough. How small? I don't know, pick it 0.01 if you really want a number, okay? For me, the picture is sufficient. I just see, okay? So there you go. If, oh, sorry, I'm not done. But don't be in a rush. Okay, so that's for x positive. Now let's do the same thinking for x negative. If x is negative, then for x small enough, I shouldn't jump the gun, huh? We have sine 3 of x is negative, right? So I'm on the other side of the world, this side. Yeah, this side. So x is negative, right? And the sine bit, sine 3 is negative as well. So the product of two negative numbers is negative. But the product of two negative numbers is positive. Voila. Bah. So now we have these two cases. It's either positive, either negative. In both cases, the product is positive. Yeah. So this thing I can say, okay, so for x small enough, positive or negative, the sign is positive, right? So I'm referring to this bit. And then by the same kind of by the identical reasoning, this thing here will be for y small enough, okay, the sign is positive, right? So the same thing. So now positive, positive, in front they have negative. So overall this will be negative for x, y in a small neighborhood or whatever of 0, 0, okay? So that's the kind of reasoning one has to do. So there, it's not magic, it's just using a little bit of calculus 1 in it, right? Okay. So now we have an option. We can stop here or we can do one more exercise. Okay. So write in chat, what's your option? If you want to go, we go. If you want another exercise, we do one more exercise. It's up to you guys. Okay, here, I'm going to do this. Huh? Huh? Okay, someone says I'm okay with either. Okay.
What is the exercise specifically?
I don't know. I'm just looking at what I gave you, and then I'll pick one, huh? Because I don't have anything worked out, but they're all kind of the same in my.
We do the one where we make
One
W
more.
ourselves.
I'll do one more, guys. Okay, here I'm going to look here at your review problems, and I'll pick one more. Oh man, just a second. Huh? Hello? Hello? Yeah. Oh, hi. It's really not a good time, though. Okay. Like in an hour. Okay. Bye. Okay. So, all right. Let's hope the exercise is correct. Here, I'm going to share my screen. Okay. So exercise 19, okay? Or 20. 19. Okay. There you go. Exercise. Okay, I'm gonna write it and then move to my screen, okay? My tablet. Show the 0, 0 is Lyapunov stable, okay? Where the system is this. I hope it's correct. I go. Okay, and W of xy is x squared plus y squared. Okay. So I'm shifting to my screen, to my tablet. There we go. Okay. All right, so 1. W in 0, 0 is 0. Check. Ta-da. 2. W of xy, which is x squared plus y squared, is positive for any xy not 0, 0. Check. And 3. Let's do W dt along a solution, yeah? So should put x of t, y of t just for you guys. So this is dw dx, dx dt, plus dw dy, dy dt. Let's see what we get. Now the mess starts. Okay. So 2x is 2x, yeah, dw dx. Dx dt is y, fine. Plus dw dy, 2y, times dy dt minus beta times x squared minus 1y minus x. Ooh, okay. All right. Which is 2xy minus 2 beta y squared x squared minus 1 minus 2xy. These guys are going away. So we end up with dw dt along a solution is minus 2 beta y squared x squared minus 1. Yeah. Good. And now they say so we have to decide, right? So is, okay, let's ask the question, okay? So is this quantity negative, so all of it, for x, y, small enough, right? So in a neighborhood, small enough of the neighborhood of x, e, y, e, which in this case is 0, 0. So that's the question we have to answer, right? Okay. So now let's see. Okay, so on one hand, we have that beta is negative. So they say beta is negative. So this means that minus 2 beta y squared will be positive for y non-zero, and y could be small or not. We don't care about that. So the deal now is to decide about x squared minus 1, right? So the one that dictates the sign actually is x squared minus 1. Okay, so now x squared minus 1 was the sign for x near 0. Right? What is its sign? Is positive or negative for x near 0? So if we're in doubt, just say, oh, but x is 0, give us minus 1. So it's negative, right? So, or if you want, take x to be 0.1 or something, right? if you don't know how to, what's the sign of the quadratic, right? So x squared minus 1 is negative for x in between -1 and 1, right? Okay, so I see some faces. Okay, so guys, we're talking about f of x is x squared minus 1, okay? So as far as I know, if I do x squared minus 1 equals 0, we get plus minus 1, correct? So if we do here on an axis x, and then we put -1 and 1, we have a change of sign here and the change of sign here. And then the rest is the same sign of the x squared minus 1 in each of these intervals, right? So for instance, if we pick an x in here, right? So let's say we choose x equals 0, we get -1. So in here, x squared minus 1 overall will be negative. Okay, it's again going back to calculus 1 or something, okay? Whereas here, let's say we choose a -2, right? So for -2, we have 4 minus 1 is 3, so it's positive. So x squared minus 1 will be positive, and the same here, right? For any thing from here on, and then you have this interval, and then you have this interval, right? So this is positive, positive, and negative here. So coming back to our problem, right? So we had on one hand, for beta negative, we get that -2 beta y squared will stay positive for any y, non-zero. And then we have x squared minus 1 will be negative for any x in between -1 and 1. So overall, dw dt, which was -2 beta y squared x squared minus 1, will be negative for any x and y in between -1 and 1 times minus infinity or infinity, or however you want to write it, right? So if it is too complicated for you because you didn't do products or whatever, right? For any x and y in such that x is in between -1 and 1 and y in R, right? So in a neighborhood of 0, 0. So overall, this implies that 0, 0 is asymptotically stable. Yay! Yay! Okay. So that's the thing. So, these kind of exercises, so you have to check 1, 2, 3, right? 1, 2. The hard part in 3 is to figure out, if necessary, the interval, the neighborhood where this is valid, or to show that there is a neighborhood there where this is happening. So for this exercise was something, remembering from calculus 1. For this exercise, again, something even from high school to decide the sign of certain functions, right? So there you go. That's how it goes. That was it.